taken is slides from the different chromatography and spectroscopy. I'm aiming for us to write down this revision and then to go through it on the slide. So chromatography, there are all of these parts that you obviously need to know. The mobile phase, we've got the stationary phase, we've got, what are these dots here? That's the origin, but these are samples. And then, say if we're interested in this one, it's called the analyte. And then how many components is this sample made out of? Two, very good. This will be the, I know, I've got the dot there. Usually they don't have the dot where they put it on. So we've got the samples, we've got the origin, we've got the distance that it's moved, and we've got the solvent front. Now, can you tell me which one adsorbed the most to the stationary phase? The blue one. Which one was most soluble in the mobile phase? Which one would have the highest RF? Red, very good. So, we're actually going to be moving on to the, first of all, I'm going to just show you the principles again. I've already written this down though. It's all about separating mixtures. All forms of chromatography rely on adsorption to the stationary phase and desorption or dissolving in the mobile phase. Smaller RF values, have they adsorbed or have they absorbed more or less? Sorry? More, very good, because they'll be lower down. How about RT, the retention time, when they come out? If it's a shorter retention time, it's adsorbed less. Okay. Principles of spectroscopy. This is just for a revision. All forms of spectroscopy. Shh, guys. All forms of spectroscopy use a part in the electromagnetic spectrum. Remember, how does the spectrum go? The longer the wavelength, what's the relationship between wavelengths and energy? And frequency?
Higher frequency, higher energy.
Very good. And shorter wavelength?
Yeah.
Okay, so when matter interacts with light, it is either... Shh. Guys, can we just stop the chatting because we do want to get through it before the pizza comes, yes? Daniel?
Yes, pizza. Continue.
Okay, so energy is either absorbed, emitted, or reflected. Do you remember absorbed if it's from low to high energy level or high to low? Absorbed. Low to high, very good. And then emitted would be? How about reflected? Nothing. It's not, doesn't take in the energy first. It just bounces off. Yep. Okay. So, guys, now we've got to add to our poster. Now, I'm going to go back on the chromatography side, and we're going to write down the... Yeah, it's the UD sort of level. They won't describe it as planar, but it means that the chromatography is in one plane. So paper and thin layer is planar, and then they have column chromatography, which is not in one plane. Okay, so there are two forms, guys, of qualitative only. There's two forms of qualitative only. What are the two chromatography techniques that are only qualitative, Daniel? Excellent. Excellent. And what do we use? Daniel, do you want to keep going? What do we use as the qualitative analysis? How can we determine what is there through paper and thin layer? Yeah, close. But what do we look at in particular about the components? Which is called? How far they travel compared to the solvent? RF, very good. So that is the qualitative analysis. So I'm going to draw that out. So let's say we've got this piece of paper here. What is, guys, can you tell me, can we copy it out as we're going through? Can you tell me what this is called, this output, the piece of paper with the dots on it? No, what's it called? A chromatogram, very good. So we can look at its chromatogram. The output is a chromatogram. Okay, then we can have two components. One here, we'll say, and one here. Then we can have, what's the distance that the solvent moves? What's that called? What's the distance that the solvent moves? The solvent front. Okay, so that's our solvent front. We then have component 1 and we have component 2, let's say. And then we have a ruler which VCAR gives us. 0, 1, 2, 3, 4, 5. Okay, it's a bit off, but you get the point. Now, what's the RF? Someone said, Daniel said that it was for qualitative analysis, but what is the RF? Rosie, do you remember how you calculated it? Distance moved by what? The stationary phase?
No. Distance moved by the mobile phase.
No. The RF, we determine it, yep. The sample, be careful, could be the mixture. What do we call it, that single thing? No, it starts with C. Component. The distance moved by component or analyte. Did you say analyte, Jordan? Did you say analyte? You can call it analyte, yeah.
So component.
Yep, distance moved by component from origin divided by distance moved, distance moved by solvent from origin. So what would be the RF value of component 1 and 2 then? RF of component 1? Can someone tell me? Two divided by 5? 1 over 4? What do you think it is? Tell me 1 over 4, put your hand up. Okay, why is it 1 over 4? Because it doesn't start at 0. Think about it, guys. If you're comparing your RFs, Gianni might put his origin up here for some reason, just because you want to. And I'm like, no, I'll put my origin down there. We can't compare ours if we're measuring from the bottom of the stationary phase. You always have to measure from where it starts moving. Does that make sense? And where the solvent starts pushing it up. Okay, so we've got RF value of 1 is 1 over 4. You can't leave it like that. You have to write 0.25. How about RF value of 2?
0.7.
Excellent. 3 over 4? 0.75. Okay, then for the qualitative analysis, you said compare RF. So qualitative analysis, guys, compare RF. Compare RF values. Now, how can we do a direct comparison, Ben? Can I just go, all right, you know, Lucy did one and she got 0.24. Yeah, that's similar to alanine, which is 0.24. What do you need to make sure you do to make the comparisons accurate?
When you're comparing the RFs that you previously recorded or with a known sample or whatever you're doing.
Yep, through the database.
Yeah.
Yep.
You need to make sure that the conditions
Excellent. You need to make sure the conditions are the same. Not all of them. Which ones can we change and which ones do we have to keep the same?
The ones that will affect the RF.
Okay, but tell me which ones. You weaseled out of that one. Which ones do we have to keep the same?
Temperature.
Temp, very good.
The solvent concentration. Or just
Yep,
the
so type of solvent. And do we have to keep our stationary phase the same? Yep. SF, stationary phase. No, P. All right, so how about the conditions that we can change? The time, very good. What else?
Stationary phase.
We can change. We can change the stationary phase. What do you mean by that though? But if we change the type of stationary phase, we will change the RF because we can change the polarity of it. But what can we change about the stationary phase?
Is this qualitative or quantitative?
This is all under qualitative only. Yeah, all under qualitative only. So what can we change about the stationary phase?
The length.
The amount?
Excellent. Amounts of components and the length. Because it's only a proportion that the mobile phase travels compared to the components. So length of stationary phase and conc of components, they won't change. Guys, if I had double one, would it move further? If I had double the concentration of one?
The dot would just be like bigger.
Yeah, it might be slightly darker. But remember, qualitative only, we can't determine how much is it. Are you guys happy with that as a qualitative measure? Okay, stationary phase. Okay, so in planar chromatography, the qualitative only. I put this as a little summary. Mobile phase in paper and thin layer is a solvent or solvent mixture. We can choose what we want. We want methanol mixed with water, make methanol mixed with water. Stationary phase, piece of filter paper versus finely powdered alumina spread over glass or plastic plate.
separate this column again and do that, or just
Sorry? No, don't write this one out. Just the one that we've got there. This one's online. Then we've got separation. Have a look. Separation depends on the attraction to the mobile phase and stationary phase. It's the same in both. Here, the samples, guys, this is something really important. Maybe add that to your chart. So paper, samples are polar samples. Thin layer chromatography, non-polar. Okay. And then we've got the RF. Qualitative analysis, compare RF under similar conditions. When we say similar conditions, we mean those conditions. Temperature, solvent, type of stationary phase. Happy with that? Should we move on to the qualitative spec? Okay. So then we've got qualitative only. What are the two types of spectroscopy that we learnt about that are purely qualitative? Very good. One more. A or AE? AAS is quantitative. AES. So the way I think ABC. The way I think about these guys are the qualitative only are the emission spec. Only looking at what is emitted by the metals. Yeah, they're always metal samples. Okay, so we've got two types. We've got AES and flame. Okay, So the flame test, how can we use that for qualitative analysis? That's kind of an easy one because you've done it. The colour that it goes, it's not really the flame is going the colour, it's the by our sample. So remember what's actually happening? When we heat it up, electrons, lots of gaps. Why are there lots of different gaps? Why are they releasing lots of different energy types? Excellent. And why is it always the same? It doesn't matter where we get the potassium from, it's always purple. It's always got the same gap in energy level, but they all have shell 2. Why isn't the shell 2 of potassium similar to the shell 2 of calcium? Rudy, you really want to answer it? No, that one. They all have the same.
I was going to say, is quantized the word for the jumping up?
Quantized. So when you're...
The word had something to do with this topic, but I can't remember what it was.
Yep. So let's say that this is your nucleus here. This is shell. This is 1s. This is 2s. Yeah. Potassium's. Shh, guys. Potassium's gap between 1s and 2s would be different to sodium's gap between 1s and 2s. And when an electron jumps up, it needs to absorb this particular package of energy. That particular package of energy is called quantized. It's defined
So you're saying it is quantized?
because it's counted. It's counted. Quantized means you can actually...
This isn't a spelling bee.
No,
So 14 electron volts is the quantized amount of energy between shell 1s and shell 2s. So remember when we went to, do you remember when we went to VU and he was saying that electron volts, that thing between the shell levels, did anyone remember his little overheads? And he had like shell, so he knew that between those two shells it was like 18 electron volts or whatever. So you can actually count it, and if you give sodium specifically 14 or whatever electron volts specific, they will jump up. If you give them 20, it's not like it takes 14 and it leaves some. It actually doesn't absorb. That's why, remember when we use AAS, we use the hollow cathode lamp? It emits exactly the gaps that the other one's going to absorb. But we'll get to that. So, flame test, we compare, for the qualitative analysis, you compare the combination of colours released. Okay. Sorry? We are going to do a little picture with that one. We're going to do it for AES. So guys, for AES, we're going to draw a little picture of what it actually looks like. We've got the sample in the flame here. It releases a combination of colours. Let's say this. I mean, I could go nuts and do all of them, but I won't. That. And then we've got something that separates it. Prism. Our eyes are not prisms, yeah. Please don't write that in the exam. Okay, then guys, it's detected by a detector and we just get these lines.
Wait, could you write that one slide?
Sorry?
Should we draw that picture? What's that?
If you want to. That's just talking about the gap between the two shells.
What's that other line that's pointing next to AES?
Oh, this is just like, let's say that we've got our sample on a stick. I'll just do that and I'll write sample. Oh, what? That's not supposed to be that colour. Yeah, that's a flame. Of course it's a flame. 12:30. So guys, the qualitative analysis. Guys, Rosie, are you writing this down? Yes, sir. It's just that if you don't understand chromatography and spec, this is a really good chance for you to get it, because I'm breaking it down. It's like, it'll be pretty pointless if you're not listening to it.
What are you doing right now?
AES. So, as a qualitative analysis, how can we determine what is there through AES? I know through the flame test you compare the colours, but through AES, what do we do?
What's the name?
Qualitative analysis. Yeah? Yes. Okay, see ya.
Bye.
Oh, have fun. Okay. Guys, come on. How can we use this? Very good. Compare the emission spectrum. So, guys, this is called, while that's called a chromatogram, this is called an emission spectrum. An emission spectrum. So for qualitative analysis, we compare emission spectra. Why is this more useful than just looking at the colour that's produced? So, it breaks the colour down into the individual wavelengths, looking at all of the gaps between the shells. Yep. Do you want to add to that, Gianni? Excellent. How can you tell the difference between a slightly darker green and a slightly lighter green? You just call it green. You write that in the book, and then, I mean, the difference between barium and copper is one's toxic and one's not, so it can be really dangerous for us. Yeah.
Does this still fall under the idea that most elements cannot be decided by above lab planes, or is this?
These are all metals. All metals.
So is this overcome, or is that still
No.
an issue here?
Still an issue. Metals only. Even
So the only
AAS.
one that overcomes that is
UV vis, because you're not heating it, they're just absorbing, it's like the coloured solutions which are absorbing energy. Yeah. Okay, so as a little revision, these forms of emission spectroscopy, we've got the flame test, we've got AES. Caitlin? Shh. Carly? Okay, for the flame test, qualitatively, we look at the combination of colours emitted by the flame. Oh, how annoying are you? Not you guys. That just turns off. It's too long. Just so angry. All right, guys, I will come back to that. But should we actually move on to qualitative and quantitative forms of chrome and spec? Yeah, that's our last one that we have to do. So here we've got, I'm going to continue on. Obviously in my poster I had qualitative up the top and I had the quantitative at the bottom, but I can't fit it all there. So here we've got the spectroscopy. So if you're writing under that column, it's under the spectroscopy column. Oh, I've got the purple here. So under the spec column, and this is the chrome column. Just continuing on. Okay, under spectroscopy, what are the two forms of both qualitative and quantitative? I give give up with the caps lock. Okay, it works out really well because for spec and for chromatography, we have two forms of techniques which are both qualitative and quantitative. And we have two forms of techniques which are just qualitative. So it actually works out quite well. What are the two techniques which are qualitative and quantitative for spectroscopy? Excellent. AAS and UV vis. AAS, UV vis. While we're here, can you guys just tell me what kind of samples we look at in AAS?
So you said the AAS is qualitative and UV vis is quantitative?
No, they're both qualitative and quantitative.
Oh, right, yeah.
AAS is atomic. Does someone want to? Yeah, have a go, Caitlin. Have a go. Yes. Spectroscopy. Atomic absorption. Spectroscopy. How about UV vis? Oh, sorry, metals we've got for AAS. For UV vis, other things. What absorbs in the UV part of the electromagnetic spectrum? Think about your gel electrophoresis and your things like that. What absorbs in the UV part? Organic compounds. Organic compounds. So UV visible is organic compounds, orange compounds, organic compounds, and what absorbs in the visible part of the electromagnetic spectrum? Think about it. We did an example here. Miss Pellone went out to Coles to buy all of these things. The Skittles. So coloured
Smarties.
solutions. Yeah, whatever. Smarty Skittles. Coloured solutions. Yeah, so remember you're green because you absorb red.
Yes.
And you reflect green.
Yes.
Okay. Sorry? You what? No, tell me. No, tell me.
No.
All right. So we've got organic compounds and coloured solutions. Okay. So we have a solution, guys. We have something that's a blue solution. We'll be using mainly orange light to see how much is there. We can do something like that. So, chromatography. What are the qualitative and quantitative techniques? Excellent. Excellent. GC, HPLC. High performance liquid chromatography and gas chromatography. Okay. So, because we said that they're both qualitative and quantitative, how can we use them for qualitative analysis? How can we use those two forms of spectroscopy, UV vis and AAS, for qualitative analysis? That's quantitative.
No, because
Qualitative.
AAS is of colour. Yes.
No, we don't use the colour. We pass the flame test. Something more accurate than that. Absorption spectrum. Very good. Very good. Very good. Extra good. No. Okay, so here we've got qualitative and we have an absorption spectrum. Do you want to tell me what's on the X and Y axis, Bridget?
Huh? Oh, wait. We do one graph with the thinners.
That's it.
And then we do a calibration one, which is linear.
Yeah, but that's for quantitative, the peaks.
We have the wavelength.
Did you want to say it?
Wavelength.
Concentrations on the left. Is that right?
No,
That's for the calibration. That's quantitative. We'll get to that one.
wavelength
Wavelength, very good.
and absorption. Yes.
Excellent.
And then on the calibration, it's absorption and concentration.
Yep. Okay, guys, we've got wavelength. Let's just say that this is our UV vis. Let's do it for UV vis. I'll tell you why, because I want to bring in this pinwheel again. Roy G. Biv. Okay, let's say something is blue. Let's say something's a blue solution. What's it absorbing? Mostly orange. It can also be absorbing a little bit of red and a little bit of yellow. Let's say that it's absorbing, quite a bit of orange and then some red. And then what would it be transmitting? What wouldn't be absorbed? Green and violet. And blue as well. And violet. So it's a blue solution.
Yeah.
I forgot that I had like 100 different colours. Okay, so we've got something that's blue, it's absorbing orange and red, and it's transmitting, I should probably have them on this other side, green. So the green's going through, transmitted.
Wait. Why have you got more colours? Oh, it's going that way.
Yeah, going that way. So basically we have a lamp here. A lamp, it's called a UV vis lamp, and it emits every single wavelength.
No way.
UV vis lamp emits all wavelengths. And then what we do, guys, we've got a detector here, and the detector actually gives us just a graph, exactly what this is. And it shows us, what will those two peaks be, do you think, that it's absorbing the strongest at? Excellent. This one might be orange, whatever that wavelength is, and this one might be red, and it doesn't absorb at green. Now, we can determine its concentration at orange and at red. Rosie?
Yes.
Do you have to do that right now?
No.
Okay. We can determine its concentration at orange and at red, but which one do we choose?
Orange.
Why?
It's directly opposite.
So, optimum wavelength, go.
Be able to absorb the lowest to get the lowest concentrations and be the most sensitive.
Yes. Most sensitive. You've got it now.
But
All right.
there was one question we did on that, and it was like, and you had to say which colour would you use or something, but they overlapped, and that's why one wasn't suitable or something.
Yes.
But I can't
So,
remember.
for example, if it was a mixture of blue
Yeah.
and what's the opposite of red? Say if it was blue and green,
Yeah.
and green didn't absorb any orange, it absorbed red and it absorbed yellow down here. Because it overlaps, let's say this was our green. Why don't I draw it in the colours? I'm so annoying, I know. Like my brain tells me to do something else. No, I do want to explain it to you. Good choice of song.
You
All right.
can only do multiple ones in UV vis spec, can't you?
But how come those two choose to go on the same, like, peak, like on the same?
They don't choose. They both absorb the same wavelengths of light because they're similar colours.
Oh yeah.
Yeah? So, Rosie, at this stage... Oh, hang on.
Is the analyte blue?
This is our analyte. I'm just trying to give an example for Rosie and I'm like, can't think of it in my head. Okay, that's better. That's what I meant. Okay, our analyte, guys, is blue, but it's a mixture of blue and green in our sample. To determine the concentration of blue, we'd have to pick the red, just because we can't tell, like say if our mixture has 90% green and only 10% blue, it's only got a tiny bit of blue, we'll be thinking there's a lot more blue there because it's picking up the green as well, because the green's also absorbing and stopping that light from going through. Yeah. Yeah.
I thought only UV spec could do two.
Yeah. We're doing UV vis.
Why do we use the red?
Because it overlaps with our, so this is a mixture of green and blue pigments. The green pigment also absorbs that orange. So we want it to determine its concentration accurately, we have to pick the highest non-overlapping wavelength. So write that down as a little summary. Pick, so for UV vis, select highest non-overlapping wavelength for the analysis. Okay.
But do we still do a graph with the angles?
You can for qualitative, yeah, just to see what's
Just
there.
like that, but without two.
Without two, that's right. Okay, so for qualitative, you compare absorption spectra. So all we do is we compare this, and I'd go, okay, let's just say we've got two spectra here. We've got something that goes like that. They're definitely not the same pigment. They may both look green to us, but they absorb at different nanometers. So it provides a fingerprint. But for quantitative analysis, it's a little different. What do we need to do for quantitative analysis? So once we've got our absorption spectrum, let's say we want to determine the amount of blue there. Once we've got our absorption spectrum, what do we do? Yes? You all answered correctly. So we make a calibration graph. We would pick the red wavelength because it's non-overlapping. Or if it's just one, you know, if we make it easier, we'd pick the optimum peak. So here we've got, we need to prepare calibration graph. But guys, on our y-axis of our absorption spectrum, we have absorbance of 40 there. Why can't I just use that to tell me the concentration? 40 what? Parts per million? It's arbitrary units. So absorption only tells you relative how much there is, not exactly the exact concentration. So you need to prepare calibration graphs. You need to pick optimum wavelength. Okay? You need to determine absorption of standards at wavelength, determine absorption of analyte or of sample at wavelength, and read off graph. Where is it? Oh, optimum wavelength. So once you've picked your optimum wavelength, you determine the concentration of your standards. You determine the absorbance of your standards at that wavelength. And that, Chris, is what you were saying. What's on the x and y axis of the calibration graph?
Concentrations on the left. Oh, on the bottom.
So what depends on what? Does the absorbance depend on the concentration, or the concentration depend on the absorbance? Yeah, the absorbance depends on your concentration. So your concentration is your independent variable. As you double your concentration, you double your absorbance. So conc is always on the x and absorbance is always on the y. Okay, so then you get a beautiful straight line, hopefully. And then you can read it off the graph. Okay. What's wrong, Zach? Determine absorbance of standards at this optimum wavelength. Yeah? So that will be this, these three dots. Then you determine the absorbance of your sample. Then you read it off the graph. Okay. Oh, beautiful that you can fit it on the page. Did I actually get a message?
I heard it.
Okay. So guys, can I just explain one more thing before we go to chromatography? I just really want you to understand this. Let's say that this is our blue pigment. Okay. Let's say that this is 10 ppm. That's our standard. We know how much there is, and we know that its absorbance is 80, whatever, arbitrary units. Then if we got 5 ppm, what would the graph look like? Would it have different absorbances? Zoe? What would it look like? Excellent. It would be half at everything.
Sorry, what's this for, miss?
I'm trying to explain how you get the calibration graph. So let's say that we've got 10 parts per million there, and that's our blue pigment. It absorbs here and here. Yeah, and it has an absorbance of 80, whatever that is. Yeah? So then we prepare something which is 5 ppm. It should have the same, like the absorbance at the same nanometers, like the same optimums, but exactly half the absorbance at everything. So once you've got your standards, guys, all you're getting is, in your exam, you'll get absorbance versus concentration, and you'll have 10, and it will have an absorbance of 80, 5, and it will have an absorbance of 40. I want you to know that it comes from this graph. It's not just magically there. It's like they actually get from the optimum peak. You could do it over here. Let's say that this is 50, that would be 25. But the only problem with that is, if you want to get even lower concentrations, you might not be able to pick them up if it's not the optimum peak. Because if it's the optimum peak, even low concentrations will still give an absorbance reading. Does that make sense? Okay, cool. So let's just finally do, it'll only take 5 minutes, chromatography. How do we use chromatography, the column ones, for qualitative analysis?
Can measure out the rate of how much comes out.
When you say how much, aren't you talking quantitative?
Oh, okay.
It's what is there? Retention time. So you know how here we did RF for planar chromatography? Here we're just going to look at what time it comes out. Does that make sense? What's that type of, that graph, what does it have on the X and the Y axis? Retention time. Versus, it's not area under the peak. It's close. No, it's close. Detector. Okay, shh, guys, please give me this last 5 minutes, yeah? So we've got detector response versus retention time. Then we may have 2 peaks here. Okay, let's compare it to this. Guys, if number 1 moved up to here, would it come out first or last? Would number 1 come out first or last? It has the shortest RF. Would it have the longest or shortest retention time? The longest. It adsorbs more to the stationary phase. So in fact, this would be 1. And this would be equivalent to 2. But have a look at the difference between this chromatogram and this one. What more information? Please, Ben and Daniel, stop talking. Daniel, you answer me then. What's the difference between this chromatogram and this one? What more information are we given in that second one that could be useful for us? Yes, we can look at the area under the peak. But, or we could look at peak height. Why do we prefer area under the peak? More accurate because you can get tailing. You've all seen tailing in your chromatograms. You can get things like that. That's equivalent to fat peaks. Doesn't all come out at the same time. So, what could you conclude from this though, qualitatively? There are 2 components. Yes, very good. But what could you determine, let's just say 6. What could you determine from that retention time? Very good, that's more quantitative. There's more there, we don't know exactly how much.
Oh, there's 2 separate compounds.
2 separate compounds. Yep. So for qualitative analysis, you compare retention times. No. Retention times. Okay, guys, what do you have to keep the same to compare these retention times? Constant, what do you have to keep constant and what can you change? Temperature, you got to keep the same. You'd have to keep the length of the column the same. You can't change the stationary phase length because why? Excellent. Because we're not looking at the proportion that the solvent goes compared to the components. So temperature, type of mobile phase and stationary phase, and also length of column. But you could change one thing really. I don't know if you could change anything else, but what could you change? The time of the run, but they come out at that particular time. Concentration, very good. Because if we had twice as much of 2, that doesn't matter. It would still come out at 2 minutes.
Oh, that's for just qualitative.
Qualitative, yeah. But I mean, you can keep those, you can change the concentration and still compare the retention times. Oh, it's just arbitrary, depending on what our detector is. Sometimes they charge them and then look at the amount of electrical conductivity of them. So the more things they have there, the higher the conductivity. So sometimes it's in millivolts and things like that. Sometimes it's in, they make a precipitate out of it and things like that, and then they look at the absorbance of it. But it's just arbitrary units. It really doesn't matter what it is, as long as it's consistent. The detection is consistent. It should still be twice as much with twice the concentration. Okay, then we finally have quantitative analysis. What do we do for quantitative? Have we got any ideas? Area under the peak has something to do with it? Hang on. Calibration graph. Is that what you're going to say? Calibration graph. So again, oh, this graph, very good. Have a guess what this graph is called. It's not a retention time graph. It's called a chromatogram as well. It's like the chromatograms are similar but different. Okay, can you guys tell me what the difference is between the calibration graphing the UV vis, you know, and AAS, so spectroscopy compared to chromatography? Excellent. Usually, actually, it's area under the peak because they measure the area under the peak. But not only that, what's another difference?
You're getting concentration both, but one you're doing basically the height of the peaks, and one you're doing the area under the peak.
Yeah, you could do the area under the peak of the absorbance thing, though. You can also do it with peak height. Let's actually talk about what the difference is between them in terms of that first step. We don't pick an optimum wavelength. What do we pick? Do we just look at we're looking at how much caffeine's there. Do I just pick anything?
Analyte.
The analyte what? It's retention time. You need to run a pure sample first, determine the retention time, same as pick the optimum wavelength. If this is caffeine and you look at the area under the peak of things at 6 instead of 2, you're going to get 0, 0, 0, 0 area under the peak because your standards won't have anything else. Remember, we picked 1.99 something or whatever for caffeine, and then when we run our standards, we only look at the area under the peak for caffeine at 1.99 minutes. Okay, so we got calibration graph. So we run a pure sample of analyte and determine retention time. And then we run standards and determine area under peak at chosen retention time. Then we run the sample. The sample will have about, it could have 50 different components, 50 different peaks. Which one do you choose?
The one at the specific RT.
Excellent. So when we run our sample, we determine area under peak at chosen RT and read off graph. But similar sort of thing in terms of the graph, but this time, as you said, I think it was polar, you have area under the peak versus concentration. Should get a straight line. Should. VCAR's nice. They usually give you something with a 0.999 correlation. Okay. I didn't really hear it. Well, how beautiful does this look? The colours look good. Sorry? Ethene to ethyl propanoate. Ethene and propane. So I'm going to go, first of all, when it's ethyl propanoate, what's it talking about? An ester. What's the alcohol and what's the carboxyl?
Propanoic acid.
Ethanol and propanoic acid. Okay, so let's try and get to ethanol. What do we have as our starting reactant? Ethene. Okay. Yes. All right, so I'm going to be doing my structural formula like this. C to C. I'm just going to do it in boxes to make it a little bit neater. So we have ethene. I'm going to do the semi-structural formula in green. CH2. Guys, can I just write CH2, CH2 for ethene? No. What do I need to do? I need to show where the double bond is in my semi-structural formula. So double bond, CH2. Then it says the name. Now my name is in purple, and that will just be ethene. Okay, I've answered everything there. Then it says What is it? How do I turn that into ethanol? Excellent. Let's start with that. Add, oh actually, I'm going to keep the colours in from what I'm adding. What's my reactant? What do I need to add? H2O, but I need other stuff as well. Excellent. Excellent. So if I add H2O, 300 degrees Celsius, H3PO4 as my catalyst, then my OH goes here and my H goes here. It's just a, what type of reaction is it? Very good. What's another word you could call it? Excellent. Addition / hydrolysis.
Miss, I could from ethanol and propanolic acid.
Sorry?
I thought ethyl propanoate came from.
Yeah, but it says your starting reactant is ethene, so you have to make ethanol first. So that's ethanol.
Yeah, sorry.
Yeah, no, that's good. Okay, then we've got ethanol. So I didn't do my semi-structural. So CH3, CH2OH, and then it's called ethanol. Why is it not ethanol?
Because the OH is always on either the end.
Excellent. There's only one possibility. Okay. Then we'll go from our other one, our is it propane? Yeah, propane. So propane looks like that.
Bless you.
I think. So CH3, CH2, CH3. And this is propane. Okay? Then what would be my next step? I've got to get to propanoic acid, but I have quite a few steps before I get there. What are the only types of reactions alkanes can undergo? There are only two types. Substitution and combustion. And we don't really want to combust it, do we?
Never.
So if we go substitution, what's the only thing we can substitute? A halogen. Okay, so let's just go with chlorine. It seems to be the most common one.
We're making propanoic acid.
Yeah, but if we start with propane, there's only a few types of reactions that the alkane can undergo. So we'd start with chlorine gas. We would then use UV light, very good. And then we get, because it's a substitution, how many products do we have? Two, very good. What's our second product, the byproduct? Which is called, oh, you guys are great. HCl. This is hydrogen chloride. Okay, and then we've got, let's just make it nice and easy for us, monosubstitution, and we'll put it at the end because we need to have our OH at the end. So we'll just make it easy for us. How many different types of possibilities are there for a monosubstitution reaction? And the names are? Yep, Daniel, shush. And 2-chloropropane. Okay. So CH3, CH2, CH2Cl. So we'd call this guy 2-chloro. Oh, sorry. Yeah, you're right. 1-chloro. Propane. Very good. Okay. Now, what's our next step?
Propanoic acid from 1-chloropropane.
Propanoic acid cannot be produced directly from 1-chloropropane. Yeah. Propanol, very good. So, guys, remember, once we add that chlorine there, how does it change the charge of the carbon? It makes it polar. And what charge does this carry now? Excellent. And it used to be negative because it used to be more, it used to be able to attract electrons more than the hydrogens. So we make this susceptible to attack by OH minus also NH3 because of the negative part of that, and H2O with a catalyst, the O part of H2O with catalyst. So which one do we choose to make our... You're likely to do NaOH because H2O you need a catalyst, and VCAR really gives you that option of having a catalyst.
Why did you add chlorine if it's ethyl propanoate?
Sorry?
Why did you add chlorine if it's ethyl propanoate?
Because we need to make propanoic acid from propane, and the only way we can do that is through this pathway.
Oh, right.
Yeah, so if you have a look at the pathway, all right, so we can add NaOH. Now, what type of reaction is this? Oh, we didn't even say that with the other one. What was it? Reaction type. Bless you. What type of reaction is this? And sometimes it's called, as Bridget would love, chlorination. I thought you said you hate it because it seems wrong.
No, I love. Oh yeah, yeah, that's true.
And this one, what's this called?
Hydrogenation. No.
We're adding NaOH to, it's again a substitution.
Sulfonation.
Sulfonation. All right. So we add our NaOH, and what goes on here? OH. OH, and then we've got, what's our other product if it's substitution? NaCl, very good. Caitlin, the one that wasn't here, is answering the most almost.
Because I want you to hurry up.
Oh.
Not as in her, like the content.
It's okay.
You told me to stop breathing, so.
There you go. So that's it. We're square now. All right. CH3, CH2, CH2OH. Propan-1-ol. Happy with that? Now we're nearly there to propanoic acid. What's the final? How can we turn propanol into propanoic acid? Oxidation. Very good. And what do we need? MnO4 minus and H plus. Oxidation. So what are we going to be making? Propanoic acid.
Are there any byproducts after the
What
substitution?
happened?
This oxidation.
No, previous substitution.
Sorry, what's wrong?
That previous substitution.
Yeah.
Wherever we put the chloride.
Oh, very true. There is another product, which is NaCl. Yeah.
Why do you have to do all these steps? Why can't you just add H2O then to the propane?
Because propane won't react with H2O. That's not a reaction. That would be propene. Propane can only react with halogens under UV light. Propane can only react with halogens under UV light. If you add propene, you could add H2O to make it propanol, and then you could just do another step to propanoic acid. Okay, we are nearly there, guys.
So we say plus MnO4.
No, that's just the reagent.
So is there any reactant?
That is, did you end up writing out the balanced reaction?
I'm still doing that for every one of them.
No, I mean, it's a redox reaction. Remember I got you to do it in class?
Yeah, yeah.
MnO4 minus would go to Na2 plus.
No, but just for these.
The only reaction is MnO4 minus. That's the oxidant.
Get in there.
you put it on the hour always.
So we don't do anything.
You just put it on, the whole thing is this, see how you're writing it out like this? That's the thing. Yep, that's why I got you to do. Alright, last one. Hang on, Bridget, I'll help you after this. So last one. How do we make our ester? What do we need? And one more thing. H2SO4. Remember, what removes water out of our skin? And it would take this and this, let's say, and it would make H2O. That would be the other product. So the other product would be H2O. What type of names? What type of name is this reaction?
Esterification.
Excellent.
Or condensation.
/ condensation. Christina, you may have studied this when we left it.
When?
Did you?
No.
You remember a lot. Do you have it there? I was like, wow.
But I didn't know that was called.
Esterification or condensation.
This what else actually gonna be like?
Yeah. But one period of it.
Can it just be one question?
One big.
That would take you out.
Well, have a look at your practice sack. That will be the best indicator.
That's a big
And when's that next like after that next one?
It'll have to be before exams. It'll be on one chapter only though.
And so that's why we only have 2 sets.
Sorry?
We only have 2 sacks next term.
Yep. So CH3, guys, I always draw my carboxyl first because when you're writing out the semi-structural formula, it makes it a little bit easier because you just go CH3, oops, that has a H there, CH2, C double O, CH2, CH3.
between the C and the O.
Here?
Yeah, do you need to put that in there?
Yeah, oh, oh no, I've asked them about that. You can choose to put it in or they don't take marks off if you don't put it in. Only if it's between carbon and carbon. They said it's not necessary. They just decide.